we'll be bringing up our first speaker, Maria Eckstein from University of California, Berkeley, who will be talking about hierarchical learning in complex action sequences. The floor is yours, Maria.
Hello, thank you so much. Like you just said, I'm Maria Eckstein, and thank you so much for having me. I'm doing my PhD with Ann Collins at UC Berkeley, and I'll tell you about a project that I'm currently working on with the title, How the Mind Creates Structure, Hierarchical Learning of Complex Action Sequences. I want to start by saying everyone agrees that we use hierarchy. For example, in the field of machine learning, there's a famous example of the 4 rooms domain. Basically, you have an artificial agent that is dropped at a random location in this blue playing field, say the green circle here, and it needs to find the red cross up there by trial and error. Trial and error means that the agent can pick one action, up, down, left, or right, on each trial, and then observe what happens. It can't look ahead. All the dark blue tiles are walls that the agent cannot cross. What happens in this case is that a standard non-hierarchical reinforcement learning agent will often just get stuck in the room in which it spawned and not find the red cross before the time runs out. Now, an easy fix for this problem is to add hierarchy. When we add the action, go to the door, to the agent's repertoire, all of a sudden it will be able to explore all 4 rooms more evenly and find the red cross. This simple example is supposed to highlight how seemingly complex problems can all of a sudden become very easy once we equip an agent with hierarchy. In this case, we use temporal abstraction, which is the ability to execute multi-step actions. Lots of research in machine learning has used hierarchy to solve complex problems, ranging from the options framework to MaxQ, pseudo reinforcement learning, MAML, R-squared, option critique, to name just a few. In psychology, research has been interested in hierarchy for several decades now. One famous example is the case of expertise. For example, in chess masters are able to remember the positions of dozens of pieces on a board, and it turns out their trick is state abstraction, another form of hierarchy. Basically, chess masters chunk constellations of several pieces into a single mental representation to save memory space and be able to remember and plan more efficiently. Recent research has put increasingly more focus on formalizing hierarchical cognition, and many researchers have proposed hierarchical Bayesian models like Josh Tenenbaum, Tom Griffiths, and more recently, many hierarchical reinforcement learning models have come up. For example, by Matt Botvinnik, Michael Frank, David Bader, and we also have a new paper that's coming out in PNAS this year. In neuroscience, there's strong evidence that the brain is organized hierarchically as well. The prefrontal cortex exerts control over subcortical regions, and in addition, the control loops between prefrontal cortex and subcortical regions themselves are organized hierarchically, such as more anterior loops operate at more abstract levels than the posterior loops. So it's not that everybody agrees that we use hierarchy, but how do we create hierarchical representations? Like in the 4 rooms domains, once we have the right hierarchical representation, problems are often easy to solve. But where does this representation come from? Some computational studies show that humans use a Bayes optimal task decomposition, but finding this decomposition usually requires full knowledge of the state space and lots of processing power and time, and humans usually don't have access to either. What we propose here is that humans create hierarchical representations piece by piece. We continuously learn new, ever more complex actions that we then add to our action repertoire. Say we are born with a very basic set of actions, like stretch your arm, move your fingers, wave your hands. This baby here might explore the world around him by randomly executing one of these actions at a time. At some point, he accidentally hits the rattle and it makes a sound. This new sound triggers the baby's curiosity. What happens next is that the baby wants to produce that sound again. He sets a goal for himself and is intrinsically motivated to reach it. Over time, he will learn how to grasp the rattle and make that sound, and he'll add this new skill to his action repertoire and use it for future exploration. In this way, we don't require a reward at every time step in order to learn something useful. We can learn continuously just by following our intrinsic motivation, which is shaped to our environment. Over time, our action repertoire expands and gets more complex, and for this violinist here, Andrew Bird, playing an entire song might just be one action in his repertoire. To test this, we came up with the following task. Participants see this machine and are told that their goal is to make stars. The machine makes a star when they type in the correct sequence of 4 keys. Say we press the orange key first, nothing happens yet. Then we press the blue key, and a gear appears in the machine. This is exciting. It's not the star we were hoping for, but at least something happened. The gear is the rattle sound for the baby. It motivates us to learn the subsequence and use it for further exploration. So this is what we do next. We press yellow again and blue again, and indeed we can get the gear back. Now let's try something different. This time we choose the purple key and the red key, and we get a red light. Same story, we want to make it work again, and it does. We now have added two new actions to our repertoire, the gear and the light. Now let's see what happens when we do both, the gear and then the light. Orange, blue, gear, purple, red, light. And the combination of the gear and the light produces a star. In the task, participants had to learn how to make 4 different stars, each with a different 4-key sequence. Crucially, each 4-key sequence was composed of the same 4 2-key sequences, including the gear and the red light. Participants first had a learning phase that looked basically like what I just showed you. Participants are told to make a specific star and get points whenever they got this star. After 400 trials of this, they do a transfer phase. What happens here is that all of a sudden, the learned rules stop working. We have 2 different conditions for the transfer phase, low and high. In the low transfer phase, we change the low rules, i.e. which keys make a 2-key sequence. In the high transfer phase, we change the high rules, i.e. which combination of 2-key sequences makes a star. If participants learn the game in a hierarchical way, low and high transfer should affect performance differently. Of course, we counterbalanced everything, for example, the assignment of keys to colors, key sequences to items, order of low and high transfer blocks, etc. We have collected 60 participants so far. So let me show you how participants did this task. I'm plotting the trial on the x-axis and accuracy, which is whether they managed to get the gold star, on the y-axis. In the beginning, participants don't get the right star, but they learn pretty fast and get up to 20% at the end of the first block. Then the gold star changes, and they start around chance again. At some point, stars repeat and participants get better and better over time. Then the transfer phase starts, and we switch out the rules, and participants are back at 0. But they recover fast and relearn the new rules pretty well. What we did next was to go through our hypotheses one by one and check each. First, we wanted to know whether participants would set sub-goals and be intrinsically motivated to execute the 2-key sequences, even though they didn't get a proper reward for them. What I'm showing here is trials on the x-axis, and I aligned them to the first time a participant executed a particular 2-key sequence. On the y-axis, I'm showing how often participants use this same sequence again. The blue dots are valid sequences, the ones that lead to a gear or light, and the red dots are invalid sequences, which do not lead to anything but have the same structure other ways. What we see is that participants were more likely to repeat valid sequences than invalid ones, as if they were motivated by the signal to repeat and practice these sequences. In the plot below, I'm showing the 25 trials of just the first block on the x-axis and the frequency of valid and invalid sequences on the y-axis. We see that in the beginning, valid and invalid sequences are equally likely. But over time, the valid sequences become more and more likely, as if participants make them their basis for exploration once they discover them. Importantly, these analyses would be totally confounded by rewards if I left the trials in there in which participants actually got a star. So I removed all rewarded trials here, and the patterns still come out. Next, I wanted to know if participants really created new actions in this game, if they would start treating valid 2-key sequences as distinct actions. If that is true, participants would show a specific pattern of response times. At the beginning of a trial, they would think about which sequence to use, then execute both keys of that sequence in one swoosh, then think again, and maybe execute another sequence. This is exactly the pattern that we found. I'm plotting the 4 keys of a trial on the x-axis here, and the response times for each key on the y-axis. Each color is 1 participant. Participants took their time to press the first key in a sequence. The second key came really fast after that. Then they think again at the beginning of the second sequence, and the last key comes very fast. This looks like participants select 2 unique key sequences and not 4 unique keys. Lastly, I wanted to look at the transfer phase and see if you have differences between the high and low condition. As a reminder, in the low condition, we changed individual keys in the 2-key sequence. In the high condition, we changed a combination of 2-key sequences that make a star. What I was interested in was whether people relearned the low-level 2-key sequences as easily as the high-level sequences of sequences. Our hypothesis was that the lower level would be more consolidated and less accessible. Basically, once a key sequence becomes an action, it would be hard to change it. We thought that the high level would be much more flexible and malleable because it has not yet been consolidated. And it looks like this is exactly what happened. I'm plotting only the transfer phase here, trials on the x-axis and accuracy on the y-axis. High transfers in red and low transfer in blue. And we see that participants relearn much faster in the high transfer phase than in the low transfer phase, and also show faster response times here on the right. This suggests that participants chunk 2 key sequences into actions, and that these consolidated actions are harder to unlearn. So in conclusion, there has been a tremendous amount of research on hierarchy over the past decades, and everyone agrees that it is beneficial and can, theoretically, solve some of our hardest problems. Nevertheless, we don't fully understand yet how humans create hierarchy. We propose that what we do is to expand our action repertoire by adding more and more complex actions, and that we use non-rewarding signals from our environment to achieve this. We have behavioral evidence that humans indeed chunk action sequences into distinct new actions and use them as a basis for further exploration. What I want to do next is to create a hierarchical reinforcement learning model to formalize this idea and explore our dataset in more detail. And with this, I would like to thank all of my collaborators on this project. First of all, my advisor, Anne Collins, and all members of the CCN lab at Berkeley. Please get in touch if you have any questions or comments. My email is maria.eckstein@berkeley.edu. Thank you so much.
Thank you, Maria. This is the applause that you probably heard from attendees if you were in a live presentation. But we do have some questions now. So the first one is from Eleanor. This might be a very general question, but do you have any predictions regarding the neural basis of hierarchical coding in the brain? Where and how would it be encoded?
Yeah, that's a fantastic question. And I'm just starting to scratch the surface of this. So there's a lot of research, both in humans and in rodents and in non-human primates, about the neural representation of action sequences and of hierarchical action sequences. And from what I've got so far, it seems that the basal ganglia play a really important role there for both learning and execution of those hierarchical sequences. And there's this study by Geddes et al., I think in 2018 maybe, where they do some optogenetic manipulation and show they really go in depth here of showing how those action sequences are represented. I can maybe put that paper in the chat if you're interested. But yeah, there's a lot of research there. So it's like mostly basal ganglia, and then I think some interactions with the prefrontal cortex in the cortico-basal ganglia loops.
Great. So we have another question. How do you know that people weren't learning hierarchically simply because your task encourages it?
Yeah, that's a very good question. I think that's always the debate. How much do you put into your task and how much comes out? So I think I definitely designed the task so that people would be motivated to learn hierarchically. And then I'm interested in how they create this hierarchy over time. So the idea is that we don't put rewards, we put some kind of information signal at the end of those two key sequences to see if that helps people learn them. A control that I've been wanting to run is basically to take away those signals, to take away the red light and the gear, and to see what happens then. Are people still able to infer the hierarchy, even if you don't give them this cue along the way? And my hypothesis is that people would still be able to learn it, but it would take them much longer. So the idea here is that we can kind of bootstrap our hierarchical learning if you pay attention to what signals the environment is giving us, and if we're intrinsically motivated to kind of learn some control over the environment as we go.
That's a wonderful answer. I think it kind of answers the next question, which is, do you think the formation and relearning of two key sequences is contingent on the feedback signal?
So is that in the transfer phase? I'm assuming the relearning of the two key sequences in the transfer phase? Is it
transfer phase, yeah.
Okay.
Or maybe even, yeah. I don't know if it is between these switches or between the transfer phase. Yeah. So each time you see there is an increase in performance and there is a drop because there is a change in the contingency.
Yeah. So when in the learning curves that I showed in the beginning, that keep going up and down, that is basically because participants are told in the beginning of each block which star they are supposed to reach in this block. So say the orange star, and then there's a green star, there's a blue star. So the reason it drops is that people might still transfer over all the two key sequences that I have previously learned, but they still need to remember or relearn how to combine those together.
Okay, and is it valid for the transfer phase also?
Yeah, in the transfer phase, I think it's really important that people get this feedback. In the low transfer phase, when we change the two key sequences, I think it is important for people to get that feedback. And all of a sudden, when they press the two keys, the gear does not show up anymore. So this is an important signal for people to relearn. But I haven't looked into that into too much detail, so that's gotta go
Okay.
into my to-do list.
Yeah, so I think we are at the end of our time. So there is one more question, but can you quickly check and answer it in the chat?
Yeah, I'll do that.
So we'll be moving on to our next speaker. We have Leonie Glitz.